What's up everyone, welcome back. Patrick here, moving on to another word problem dealing with exponents. Now before getting into this, I want to mention that this problem here, very similar to the previous problem that I did. And so because the process is going to be fairly similar, I'm going to go through this one a little bit quicker. So before watching this one, make sure you watch the previous one because I go into a lot more detail of how to go about these kinds of questions, especially when creating these equations here. So when I'm going through this, I'm assuming that you've watched the previous video. If you're watching this on YouTube, then you can go to the course website. It's going to be in the description box, the link to the course website where everything is following in order. I highly recommend watching the videos there because some videos have a lot of carryover of concepts from previous ones. All right, so make sure you watch that video before watching this one. So what's happening is we have a certain bacteria again, but in this case, it has a half-life of 2 hours, meaning that instead of growing like the previous bacteria was, the previous bacteria we had 2 that were doubling, this one is decaying because it says it has a half-life of 2 hours, meaning that it's decaying by half of its amount every 2 hours. We're going to show what that means in a table soon. And then it also starts at an initial mass of 1,000 milligrams. So in part A, approximately after how many hours will the mass be 10% of its initial mass? And then in part B, we have to represent the mass of the bacteria as an equation where X is going to represent either part 1, the number of half-life periods, or part 2, the number of hours. So again, similar format to creating these equations over here as the previous video. So like I did in the previous video, let's start with a table, right? That's going to help us answer these questions. It's going to give us a nice sort of breakdown of what's happening. So what we're going to do is we're going to have time on one column, right? Actually, in this case, the time, let's label it. It's going to be in hours. The previous one was in minutes. This one's going to be in hours. And then we're going to have the quantity or the mass of the bacteria, and that's going to be in milligrams. So initially, what's happening at time 0, it's starting with an initial mass of 1,000 milligrams. And then what's happening is after 2 hours, this mass is decaying, right? So it's getting smaller. And after 2 hours, it has a half-life of 2 hours, meaning that the mass after 2 hours is going to be 500. And then in the next 2 hours, right, so at the 4-hour mark, it's going to be 250. At the 6-hour mark, it's going to be 125. At the 8-minute mark, right, it's going to be, what, 67.5? No, 62.5, sorry. Right, et cetera, and you would just follow that pattern. So that's what's happening in a table with this bacteria. Now, in part A, we're asked, when is, after approximately how many hours, is the mass going to be 10% of its initial mass? Well, the initial mass is 1,000. So what's 10% of 1,000 milligrams? Well, we would just take the 1,000 multiplied by 0.1, right? Remembering your decimals, so that's the same as 100 milligrams. So basically, another way to word the question of part A is, after approximately how many hours will the mass of the bacteria be 100 milligrams, right? Which is 10% of the initial mass of 1,000. Well, if we look at the table, when is it going to hit 100? It's going to be in between the 6 and 8 hour time frame, right? And it's kind of, let's say, in the middle. This is not linear, so it's not a good way to think about it, but different ways. They're only asking approximately, so approximately, well, saying between 6 and 8 hours is not approximate. That's definitely happening, right? As we could see from the table, because at the 6-hour mark it's 125, at the 8-hour mark it's 62.5, so it's somewhere between 6 and 8 hours. If we were to approximate it, we could say approximately 7 hours, maybe let's say halfway. Okay, it's not going to be exactly halfway because this is not like linear, okay, if that makes sense. It's exponential, but we could say just from looking at it, approximately 7 hours, definitely between somewhere 6 and 8 hour, between that 6 and 8 hour mark, it's going to have a mass of 100 milligrams or 10% of that initial population. Okay, so you could get that from the table. Now in part B, what we're going to do is we're going to create equations. Now we're going to create two equations. So first we're going to let x equal the number of half-life periods. And as we did in the previous example, what we could do for that x values, we could create another column here. So we could say the number of half-life periods. So instead of looking at the specific time in hours, we're just looking at the number of periods that the mass is decaying to half of its amount. So initially, there's no half-life periods that have gone by, but then the first half-life period, right, it's going to go to 500. The second half-life period is going to go to 250. The third, the fourth, etc. So in part one, we're letting x be this column over here, the number of half-life periods, not the time, right, over here, this column. And then we can let, let's introduce another variable. We'll let m equal the mass. You can let y equal the mass as well. I'm going to let m equal the mass, so this here is going to be m. And so to represent an equation for part one here, where x is this column, we can say that the mass, it's going to be equal to the initial population of 1,000. Now, what's the base going to be? I mentioned this in the previous video. In the previous video, we were doubling, right? The bacteria was growing. We were given the doubling time of it, so that base was 2. Well, now we're given the half-life of it, meaning it's decaying. And so the base here in this case is going to be 1/2, like that. And then if we let x equal this column, well, all we have to do is take it to the power of x, like that. So that's going to be the equation for part one in part B. And then you could test it as well. So we can take this equation, we could plug in these x values and see if we get these corresponding m values. So if we plug in 0 for x, 1/2 to the power of 0, or anything to the power of 0 is just 1, times 1,000 would give us 1,000. What if we plug in 2 for x? We have to do the exponent first, right? So we'd have 1/2 to the power of 2, which if we take a fraction to the power of 2, it's like taking the numerator to the power of 2 and then the denominator to the power of 2. 1 to the power of 2 is 1, 2 to the power of 2 is 4. So that would be 1/4, then we have to multiply it by the 1,000. That's going to give us that 250. Right? We could do it for all of these over here. So we could plug in 3. 1/2 to the power of 3 would give us 1/8. 1/8 times 1,000 would give us that 125. Right? So comparing it to the previous video where we were dealing with the doubling time, really the only thing that changed, well, the initial population changed as well, but the total format of it, the base really is all that changed, right? Instead of having a 2 over here, we're dealing with a decaying substance. So this would be 1/2, right? And so that base, if you're dealing with a decaying substance, this is covered more in grade 11 in detail, but if you're dealing with a decaying substance, basically this base over here, it's going to be between 0 and 1. Because as long as this base is between 0 and 1, it makes this initial population go down, right? Which is expected if a certain bacteria is decaying. Now, if it's increasing, if it's growing, right, whether it's doubling, tripling, whatever, if it's growing, then this base here, it's going to be greater than 1. That would ensure that that initial population is getting bigger and bigger, right? So 1/2, that's 0.5 in decimals. Notice that that's between 0 and 1. So any base that you put here between 0 and 1, it's going to make that initial population go down. Any base that you put here greater than 1, it's going to grow that population. That population is going to get bigger. Okay, so that's part 1. Now, what if we let in part 2, let's do part 2 down here. So in part 2, what we're going to do is we're going to let x equal the number of hours that have gone by. So instead of letting x be this column, x is now going to be this column. So very similar again to the previous video. I keep mentioning that previous video as I said I would, referencing it. Initial population stays the same, right? We're still dealing with a half-life, a decaying substance. What's going to change is the format of that exponent. Now what we really want is that exponent over here to end up being this column, right? So we know that if we plug in 1, for example, we're going to get 500. If we plug in 2 over here, we're going to get 250. If we plug in 3 over here, we're going to get 125. We already confirmed that over here when we just let x be this. But now we're going to be plugging this into the exponent, right? But we need that whole exponent to be this. So notice, what's the relationship here? Well, we're just dividing by 2, right? So what we can do is we could take whatever time we're going to throw in there, right? That's going to be x, and then we're going to divide it by 2. This here, it's the half-life period, which is 2 hours. If this was, for example, 3 hours, this would be 3. If this was 4 hours, this would be 4. That's how this exponent relates to the scenario. And then same thing in the previous question when we were dealing with the 2 doubling times, that's where the doubling times went for both bacterias. And so now we could test that again. If we plug in 0, 0 divided by 2 is 0, 1/2 to the power 0 is 1, times 1,000 gives us 1,000. What if we plug in 2? 2 hours, 2 divided by 2 is 1, 1/2 to the power of 1 is 1/2 times 1,000 gives us 500. If we plug in 4, 4 divided by 2, 2, 1/2 to the power 2 is 1/4. 1/4 times 1,000 gives us 250. So that's what the equation would be if we let x be the number of hours. All right, so you got to be really careful, as I mentioned before, what they're asking the equation to be in terms of. If they're saying let x be in terms of the number of doubling periods or the number of half-life periods, it's a little bit easier because that exponent is just going to be that x value. But if it's, for example, the actual time, then you got to be careful because you got to do a little bit of an adjustment to that exponent.